Hello, hello, you beautiful people. I hope you're all doing well. If you're not, you soon will be, because we're going to do some more chemistry. Today we're going to have a little look at homologous series and the alkanes. So what are we going to be looking at in today's video? Well, as we've said, we want to be able to appreciate what homologous series are, and in order to do that, we need to understand the first homologous series that we're going to have a little look at, called the alkanes. And we also need to get down a little definition of what a homologous series is. We'll go through and describe some properties and uses of the alkanes, and we'll finish off by talking about what saturated bonding means. Now that phrase homologous series is probably a new one to a lot of us, and there'll be a lot of new words throughout this video. Don't get too worried about it though, you will soon remember them and be familiar with them all. So to put a little bit of context and flavour into homologous series, we can have a little look at these pictures. Well, what are they? Well, they're obviously all families, and that's pretty much all a homologous series is. It's just a family of chemical compounds. Chemical compounds that have been grouped together based upon their similarities in structure and in properties and uses. Do we know any of these families? I'm pretty sure the Simpsons is the middle one. So I think it's worth at this point to kind of stop and to get a proper definition written down here for homologous series, exactly what the SQA expect you to remember. Now here's the definition that you are expected to know in full and to be able to recite whenever you're asked about homologous series. Now homologous series is a group of chemical compounds which have the same general formula. Now we'll talk about what that means in a lot more detail pretty soon, and similar chemical properties. So that's our definition that we need to know. A homologous series is a group of chemical compounds which have the same general formula and similar chemical properties. So what are the important parts in this sentence? Well, here they are here. The same general formula and similar chemical properties. We just have to remember this as a sentence. A homologous series is a group of chemical compounds which have the same general formula and similar chemical properties. Now I'm not going to apologise for repeating that again because we need to know it. A couple of ways to kind of help you remember it. There's no really great ways. I normally say something like same gen sim chem, and maybe that's a little bit easier for you to remember those kind of four little abbreviated words. Same gen sim chem, and it just means the same general formula and similar chemical properties. Now throughout this topic we're going to have a little look at quite a few different homologous series or families of chemical compounds. The first one we're going to have a little look at is the alkane family. Well, the alkane family then, what is it? Well, it's a homologous series. It's a family of chemical compounds with, you guessed it, the same general formula and similar chemical properties. Now, why have I got those last three letters highlighted like that, A, N, E? Well, like with most families, to identify them you can have a little look at their second name and infer that they're part of the same family. Well, with chemical compounds it's very similar. We just look at the end of the word, and if it ends in A-N-E, well it must belong to this homologous series called the alkanes. And that ending to the name, that A-N-E, is going to become very important when we start to draw and to name all the different types of homologous series. We really need to be focusing in on those last three letters. And lastly as well, they all look very similar. And what I mean by look, well I don't just mean their English spelling names, I also mean we're going to draw these out in something called a full structural formula to show all the different bonds between the carbons and hydrogens between these molecules. And you'll see that they do all look very similar. Now I just mentioned there that our alkanes are made up of carbons and hydrogens, and from last lesson we learned that, well, if a compound only contains carbon and hydrogens, it's a hydrocarbon, and this is exactly what the alkanes are. They're a type of hydrocarbon. So our alkanes then, as we've discussed, this is the first homologous series that we're going to have a little look at, they all end in A, N, E. That's how we can identify them. And there'll be a few of them that we're going to have a little look at here that will be quite familiar with to you. You'll know them already. So let's have a little look at a couple of examples then of some chemicals that are part of the alkane family. And here's the first one. We've heard of this before. Methane or methane. Well, we use that in cooking, also in heating as well in our homes. We use it in the school, Bunsen burners, etc. We've talked about it before. We're familiar with this compound, and it's part of our alkane family. How can we tell? Well, look at the last three letters, A, N, E. There's the clue. Another one that we might be familiar with as well is propane. Again, ending in A-N-E. It's part of the alkane families, and it's used in kind of gas canisters for barbecues or camping, etc. It's quite a useful fuel. And speaking of fuels, another alkane that we might be familiar with is octane. Now, octane is used quite a lot in petrols. You've probably heard of maybe high octane petrols or high octane fuels, and this is where this comes from. If a petrol's got a lot of octane in it, it's described as being high octane, and it helps with the performance and the burning of the petrol. Now then, let's think back to the start of the video when we talked about our definition for a homologous series. Now I can feel you all rolling your eyes already because I'm about to repeat it. A homologous series is a group of chemical compounds with the same general formula and similar chemical properties. We've not really talked about this general formula yet. What does that mean? What is a general formula? Well, the general formula for the alkane family is CnH2n plus 2. Now that might seem quite unusual right now, but if we have a little think about this, this is kind of something that's maybe quite familiar to us if we think in a more mathematic setting. We've got these n's, which we'd normally probably use x's in maths for representing some number that we don't know. In chemistry, we're just using an n to represent that. And what this allows us to do by having a general formula, if we know the number of carbons in an alkane, we can also work out the number of hydrogens that the alkane will have. And that's all a general formula is used for. It's for helping us figure out how many carbons and hydrogens we have, and if it fits into this formula here, CnH2n plus 2, then it must be an alkane. Now this general formula, CnH2n plus 2, is one that we have to remember. We have to commit this to memory. Whenever you are asked what is the general formula of the alkanes, you need to immediately reply CnH2n plus 2. It's just one of those things that we need to know. So let's have a little look at it in practice now. Let's say that we have an alkane, and we know that in the alkane there are 5 carbons. We know that within the alkane there are 5 carbons, so that just means that this number n is equal to 5. So C5, just replacing that n with the 5, we'll have H2n, which we're replacing now the n with the 5, so it's H2 times 5 is a little sum plus 2. And if we complete that sum, we get C5 H2 times 5 is 10 plus 2 is 12, C5 H12. Now what we have here is called the chemical formula or the molecular formula for this alkane. Now this is the 5th member of the alkane family. It's got 5 carbons and it is called pentane. Now see what I've done there? I've gone from the molecular formula or chemical formula into the name of a chemical, pentane. That's what we're going to work up towards throughout the next couple of minutes in the video, and we're also going to want to be able to change that name into a structure as well, showing all these carbons are 5 carbons and showing all the hydrogens are 12 hydrogens bonded to the carbons as well. So this is what we're going to be able to work towards, and it looks kind of complicated, but once we get some practice at it, it is very straightforward. Trust me, you'll quite enjoy this. Well, maybe that's going too far. But anyway, back to this general formula here. We need to remember this CnH2n plus 2, and here's a little example of us using it now. We sub in 5 for the N, and it will help us work out the number of hydrogens. Let's have another little go at using this general formula just to make sure that we're comfortable with it. Let's say this time that instead of having 5 carbons, we have got 8 carbons. So N this time is equal to 8. So let's get our molecular formula or chemical formula using the general formula. So we can say it's C8, just replacing the N with 8, H2N, or 2 times 8, plus 2. And if we finish that, we've got C8H18. Now we've already had a little look at this, or talk about this compound earlier. This is octane. Ends in ANE, must be an alkane. So that's our general formula for the alkanes. We need to remember it, CnH2n plus 2. Now let's go and have a little look at all the members of the alkanes that we need to know. And we need to know the first 8. We need to know from methane all the way down to octane. Now here's our first member of the alkanes, methane. The chemical formula or molecular formula is CH4. And here's our 3 things that we need to know about each and every alkane. We need to know their name. We need to know the chemical formula, and we need to know how to draw out something called a full structural formula. So here's the name, methane, here's the chemical or molecular formula, CH4, and we need to be able to draw this structure here, showing all the carbons and hydrogens. We'll work up towards that, so don't worry about not understanding it quite just now. It will start to piece together quite soon. So methane's our first member of the alkane homologous series, and it only contains 1 carbon. Let's look at the second member now. And here it is. Here's ethane. Have a little look at it. Look at the last 3 letters. What homologous series does it belong to? Well, it ends in ANE, so it's obviously going to be an alkane. How many carbons has it got? It's got 2 carbons. So methane had 1, ethane's got 2. Now let's have a look at the number of hydrogens, and remember our general formula for the alkane homologous series, CnH2n plus 2. And let's put together all the evidence that we've got here, and just to confirm that this is a member of the alkane family. Yes, it ends in ANE, so it's pretty obvious. But what happens if we weren't privy to this name? We only had the chemical formula here. We only had C2H6. Does that fit in to our general formula? When N is 2, do we get 6 hydrogens? Let's check. So C2H2 times 2 plus 2. Yeah, that's working out. This must be part of our alkane family. And again, we've got our full structural formula, which we work up to be able to draw relatively soon. It's pretty straightforward. I always call this counting to 4, kind of chemistry counting to 4. If you can count to 4, you can do this kind of chemistry. Every carbon makes 4 bonds, and each line represents a bond. So as long as we've got 4 bonds on each carbon, we've drawn a full structural formula correct. There's a little bit more rules to it than that, but that's the general idea. And here's our third member of the alkanes, propane. We've got its chemical formula, C3H8. It fits into CnH2n plus 2. It fits into the general formula of the alkanes. It must be an alkane. And here's its full structural formula as well. Now, as I said before, we need to know the first 8 members of the alkanes. And here they are here. Methane, ethane, propane, butane, pentane, hexane, heptane, and octane. Now there's a number of different ways that I'm going to go through with you on how to remember these, because it is very important that we remember them, and especially the order in which they're in as well, and that'll become quite relevant in a second. Now the lazy way to remember these is just to go to the data booklet and go to page 9 of the data booklet, and you'll see a table like this about halfway down the page, and it has the names of our alkanes. It's got methane, ethane, propane, butane, pentane, hexane, heptane and octane, and beside it it's got the melting and boiling points, which aren't too important, but the names of the compounds are very important and we need to remember them. Now this is the lazy way in remembering it, because when we come on to look at the other homologous series like the alkenes and the cycloalkanes and the alcohols, etc., they're not in the data booklet, only the alkanes in the data booklet. What we need to focus on is the start and the end of the name of the compound. So as we've already discussed, the last three letters, A, N, E, that tells us what family, what homologous series these compounds belong to, and they're all alkanes. But the first half of the name of the compound, the meth, the eth, the prop, but, pent, hect, etc., they tell us how many carbons are in the compound, and that is so important as well. So we really need to be able to associate something like meth as meaning one carbon, or eth as two carbons, prop, three carbons. Now I think instead of just relying on the data booklet, it's much more important to remember these prefixes. Prefix is just something that goes at the start of the word to give you more information. And in chemistry, when we've got prefixes like meth, eth, prop, but, etc., they tell us how many carbons are in a compound. We've already looked at suffixes at the end, these A, N, E, telling us it belongs to a different homologous series like the alkanes, but the first part of the word is very, very important, and we need to know and to commit to memory what each of these prefixes mean. So our first one here, meth, well what does that mean? That means that we have one carbon. Eth means two carbons. Prop, three carbons. But, four carbons. They are probably the hardest ones to remember, the first four, because then after that the next four have prefixes that we've already seen in maths when dealing with shapes. Pent means five, like a pentagon, a five-sided shape. Hex means six carbons, like a hexagon, a six-sided shape. Hept is seven, and oct is eight. So the last four are probably more familiar to you than the first four, but we need to be able to associate the prefixes with the number of carbons, because this could become so important when we're trying to draw out our different compounds. Now, as I said, we can rely on the data booklet and use that to help us remember what these prefixes mean. They're in the correct order, starting with meth at the top down to oct, so you could just say, well, the first one means one carbon, second one means two carbons, etc. The way I was taught it and the way I remember it is by a little mnemonic. It is monkeys eat peanuts but prefer hot dogs. Now that's how I remember the first six. This is how I remember up to hex, using this little sentence here. Monkeys eat peanuts but prefer hot dogs. And what's the point in this? Well, it helps us remember the order of these letters. M for meth, E, eth, P, prop, B, but, etc. And that allows us as well to remember the number of carbons. And then I suppose with the last two, maybe you can think of two more words to put on the end. I just kind of remember them as they are. Feel free to come up with your own way to remember them, but you've got to do it. You need to commit these to memory. So let's cycle back up to our alkanes and the 8 that we need to remember, and let's try and piece everything together that we've talked about, the general formulas, the prefixes and the number of carbons, etc., and we'll try and figure out the molecular formula for each of these alkanes because we need to know them. We need to know the names, the molecular formula, and how to draw them. So here are the names. Let's have a go at figuring out how many carbons and hydrogens each one would have to give us our molecular or chemical formula. So meth, we've had a little look at that just before. What does that mean? Well, that means that we have one carbon. That's what meth means. The last three letters, A, N, E, tell us it's an alkane, and we know that the general formula for the alkanes is CnH2n plus 2. So then if we use that knowledge and our knowledge that when we've got methane as being one carbon, how many hydrogens would we have? So we would have H 2 times 1 plus 2, which would give us a number of 4. 2 times 1 is 2 plus 2 is 4, and I can write that properly now as the molecular formula. That should be a U in there, apologies. Molecular formula. So methane is CH4. We don't write the 1, don't write the 1 in chemistry, people will laugh at you if you put a 1 there. We just put a C to represent one carbon, and there it's there, CH4, molecular formula of methane. Let's look at the next one now. Eth, we know that eth means that we have 2 carbons, so it's going to be C2. Using our general formula, CnH2n plus 2, when we change this n to 2, we've got 2 times 2 plus 2 is 6. And it's that easy. Prop, well, we now know that means we've got 3 carbons, so when C is 3, using our general formula, how many hydrogens do we have? We've got 2 times 3 is 6, plus 2 is 8. And we can go on and down and fill in the rest of these now. But means we've got 4 carbons, and we would therefore have 10 hydrogens using our general formula. Pent is 5, and we would have 12 hydrogens. Hex is 6 with 14 hydrogens. Hept is 7 with 16 hydrogens, and last but not least we've got oct with 18 hydrogens. So see how I've used the prefixes there to figure out the number of carbons, and I've then used the general formula to figure out the number of hydrogens. So we've looked at the names, we've looked at the molecular formula, how many carbons and hydrogens these molecules have. Now we can use that molecular formula to draw something called a full structural formula. Now this shows all the carbons and hydrogens and all of the covalent bonds between the carbons and hydrogens. And it's relatively straightforward if we remember just a couple of little rules here. And it's how many bonds each atom makes. Now carbon is in group number 4 of the periodic table. It's got a valency of 4, so it makes 4 bonds. It's missing 4 electrons from having a full and complete outer shell, so it wants to share 4 more to make 4 bonds. Now hydrogen's in group 1, it's got a valency of 1, and hydrogen only makes 1 bond. So let's have a little look at these structures now in terms of drawing them out fully. So let's look at the easiest one, the first one, methane. Meth meaning 1, we've got 1 carbon, it's ane, so it's an alkane, and if we were to draw this out, CH4, to show all the bonds, we would draw a carbon with 4 lines coming out to it. Now these lines represent shared pairs of electrons, or our covalent bonds, between the carbons and the hydrogens in methane. And there's the full structural formula for methane. Each carbon has 1, 2, 3, 4 bonds. Each hydrogen has only 1 bond. Let's look at the next one, ethane. I always start by drawing out the carbons first. It makes it a lot easier. So let's do our 2 carbons. There's 1 carbon and it's bonded to our second carbon. Now each of these carbons now has one bond. This has got one bond, this has got one bond. So they each need another 3 bonds to make sure that each one has 4 bonds. And then we put in the hydrogens, our 6 hydrogens. 1, 2, 3, 4, 5, 6. Now normally when I'm teaching this I do it on the board, and it's a little bit easier to write on the board than it is with this mouse. And I always emphasize how important it is to make sure that your diagrams are as neat and as tidy as possible, because you don't want to lose silly marks. You want to make sure that the bonds are going exactly to the hydrogens and exactly to the carbons. This one here is not very good. That's not a very good example. The other ones aren't too bad. So you want to make sure these drawings aren't scrappy like mine, but they're as neat as possible. Last one here, propane. We've got 3 carbons, so we'll draw out 1, 2, 3 carbons in a row. We'll pop in the rest of our bonds to make sure that every carbon has 4 bonds. Let's just check. 1, 2, 3, 4. That carbon's fine. 1, 2, 3, 4. That one's fine. And 4 here as well. And then we're going to put in our 8 hydrogens like the molecular formula suggests, since this is C3H8. And I'm taking my time here. I could rush this and just hammer in the hydrogens, but I want to make sure that it is as neat as possible and the bonds are going exactly where they're supposed to be. Now it's not too important on a simple compound like this, but we're going to get more and more complicated, so make sure you've got these good fundamentals down right now. And from there, from a full structural formula, we can sometimes write something called a shortened structural formula. You know, chemists, we're notoriously lazy. We don't always want to be writing out every single bond when we could draw it in a shorter and quicker fashion. So a shortened structural formula, the clue's in the name. It's still a structure. You still have to convey some structural elements to the compound, but it's a lot shorter than our full structural formula. So let's have a little look at changing these full structural formulas into a shortened structural formula. So for a shortened structural formula, all we're doing is we're going to look at each carbon and write down what it's bonded to, but without drawing the bonds. And you'll see what I mean in just a second. Now the first example here, methane, is probably not a very good example. It'll become more obvious when we get down to ethane and propane, but let's go through the steps. So here's our full structure. To draw a shortened structure, we take the first carbon, well it's only got 1, so here it is here, and we write it out. And then we look at what it's bonded to. It's bonded to 1, 2, 3, 4 hydrogens, and we write those down. Now, yes, that is the exact same as the molecular formula, but that's the only time that this will be the case. Let's have a little look at ethane now, and you'll see how the shortened structural formula does differ from the molecular formula. Let's look at our full structure. Let's look at the first carbon and write it down, C. Let's write down what else it's bonded to. 1, 2, 3 hydrogens, so it's CH3, and now we go on to the second carbon. Write down the carbon, write down what it's bonded to. 1, 2, 3 other carbons. There we go, CH3, CH3. Now you can see that this differs from the molecular formula here, and it just shows the full structure in just a shorter manner. We can still kind of imply and see what's going on with the shortened structure in terms of the full structural formula. And let's look at a little last example here. We take the first carbon, C, write down what it's attached to. 1, 2, 3 carbons, so it's CH3. Then we go into the second carbon, write it down. Write down what it's bonded to, CH2. Go to our final carbon, CH3, because that's got 1, 2, 3 hydrogens on there. And here's our shortened structural formula for propane. I would like you to maybe pause the video and have a little go at completing this table here that would normally be in your pupil booklet. What we're wanting to do, or what you're wanting to do rather, is to use information that's been given and to try and fill in the blanks. So use the molecular formula here, C5H12, and think of, well, what name would the corresponding alkane be, and then have a go at drawing its formula. Right, let's have a little go at answering this table then. So the first one, we don't know the name, but we do know the molecular formula, and it is C5H12. Now the C5 tells me, if I remember my prefixes, monkeys eat peanuts but prefer, that's the second P, so that must be pent. And as we know, a five-sided shape is a pentagon, and it's probably quite an easy one to remember. What will the rest of the name be? Well, they're not always going to be alkanes, so we can't just always write down ANE. Yes, they're the only one that we've learnt so far, but what we should be doing is checking the general formula against the molecular formula. Now, this molecular formula corresponds to the general formula CnH2n plus 2, which is our general formula for our alkane. So this has to be pentane, has to be an alkane. It's got 5 carbons, so it's pent, and it corresponds to that general formula, so it must be an alkane. The structure, for drawing the full structural formula, we're wanting to draw our 5 carbons. Remember, every carbon must have 4 bonds. This one only has 1, so let's put in another 3. This one's got 2, that one's got 2, this one's got 2, and that one's only got 1, so it needs another 3. And then we can put in our 12 hydrogens. Remember, you don't want to draw your drawings as scrappy as I am. It's the computer, trust me. And there we go, our full structural formula, which can then be converted into our shortened structural formula here. Next one, hexane. We've got a name this time and no molecular formula. We know that the prefix hex means 6 carbons, so we're C6. Ane, well, that tells us it's an alkane, and it's got this general formula CnH2n plus 2, so we do 6 times 2 plus 2 is 14. And there we go, we've completed this row in the table. There's the corresponding full structure, there's the corresponding shortened structure. Back to working backwards here, we've got C7H16. When we've got 7 carbons, that means the prefix is hept, and it is an alkane again because it corresponds to CnH2n plus 2. Drawing out the full structure here, I'll try squeeze it in as best I can, not much room. We're drawing in our 7 carbons and making sure each carbon has 4 bonds. Now I've fallen into a trap here that a lot of people do when they're writing these really quickly. This no longer really looks like a C. It's kind of hard to tell, it looks more like an L. Make sure your letters look exactly like the symbol of the atom you're trying to represent. Normally it's the hydrogens that people draw as N's or K's or whatever. Take your time, pop them in correctly. And we're just filling this out to make sure every carbon has 4 bonds and every hydrogen has 1. Last one here, octane. Oct is our prefix for 8, or C8H18. And now we're going to draw our shortened structural formula, looking at each carbon and then just popping in the hydrogens that it's attached to. Now I'd probably, when we've got a long compound like this, it's very easy to kind of get confused with your positioning. Just cross them out as you go through. There's the first one done. First carbon's got 3 hydrogens on it. Let's go on to the second one, which is CH2. Cross that one out. It's done. Go on to the third one, CH2. And go all the way along until we have drawn out our our shortened structural formula. How many have we got now? 5. 3 more to do. Oh, that should be a 2. I'm running out of room here, which is fine because it allows me to demonstrate why we've got this OR written down here. So I would always, this is just the way personal preference, I always write it out like this, but a lot of people think that it takes up too much space and they would rather write it in this format here, where if we've got something that's been repeated over and over again, like these CH2s, so we've got 1, 2, 3, 4, 5, 6 CH2s, we can actually just put them in brackets. So at the start we've got our CH3, we've only got one of those, so there's there. We've got 6 CH2s, so bracket CH2, 2 end bracket, put a little 6, and then our final CH3. The reason I don't really like doing this is because my brackets look like C's and it looks a little bit confusing in my handwriting, but whatever you prefer, you go ahead and the last thing we're going to talk about here is saturated bonding and what saturated bonding means. Now to show you what it means, let's just draw out the fourth member of our alkanes. 4 carbons, all our hydrogens, and our fourth member of our alkanes is butane. Now let's have a little look at the structure and let's look particularly at the bonds represented here, because what we're talking about is saturated bonding. Now saturated bonding, what does that mean? Now I'm going to draw a big S here and write down the word saturated because this is the way I remember it. Saturated bonding, big S, means that the compound only contains single bonds. And what does it mean by single bond? Just one line. When we come on to look at the alkenes, which we will, they have something called a carbon-to-carbon double bond, where we've got 2 lines in between the compound. We don't have any of that in our alkanes. Now, alkanes are saturated because they only contain single bonds. So they are saturated. This is just another little word that we need to add to our arsenal when talking about and discussing hydrocarbons and homologous series. Saturated compounds only contain single bonds. They only contain carbon-to-carbon single bonds. Another way to think about, or to help you to remember saturated bonding, is to think about the word saturated itself. It means normally like you're full of something. If you went outside, let's say on a wet day, and your clothes got really, really wet, they would be saturated with water. Your clothes would be full of water. In this case, we can think of the compounds being saturated with hydrogens, full of hydrogens, weighed down with hydrogens, if you will. So that's another way to think about this word saturated. They're full of hydrogens. When we come on to talk about unsaturated bonding, when it's not just single bonding, you'll see that there's not as many hydrogens. So that's another little way to think about it. And that's probably a good place for us to end the video. I know I've thrown a lot of new information at you, a lot of chemistry jargon. Please take your time in going through the video, go through it a couple of times, take your own notes and use it to complete the exercises that I'll post as well. I hope to see you all really soon and I hope you're all keeping well.